Welcome back to Algorithms and Uncertainty. We've seen that randomized online algorithms can often perform better than deterministic ones. And for deterministic algorithms, it is usually pretty easy to come up with lower bounds. So we've, for example, seen this in the case of ski rental in the very first lecture. But what about randomized algorithms? How do you show that there is no good randomized algorithm that gives you a certain competitive ratio? Well, this is somehow difficult because you have to argue about the internal randomization of the algorithm, and you do not know in advance what the algorithm will do, so you cannot construct a difficult input sequence. Today we'll get to know Yao's principle, which is actually a almost trivial observation, but it is extremely helpful to lower bound the performance of randomized algorithms by, instead of talking about randomized algorithms, you then talk about deterministic algorithms. But these deterministic algorithms are you study on random sequences, random input sequences. Let's first define the notions that we'll use. Let's prove Yao's principle, and then afterwards we'll apply this to online set cover and also to ski rental to then show that our algorithms to some extent are indeed optimal. To define Yao's principle, we first need some basic definitions. Namely, we'll have script A as a class of deterministic algorithms and we'll have script X as a class of instances. We assume both are finite. This is actually not crucial, but it just avoids for us, it just simplifies our life today. Indeed, we could also do this with infinite classes, but to keep things simple today, let's just assume those are finite. And then we say that algorithm A, small a, from this class, incurs cost C of A comma X on instance X. Good. Now, the worst case for any deterministic algorithm, the worst case cost of any deterministic algorithm on any of these instances, those would be just the maximum over all small a, maximum over all small x, this C of A comma X. But what about a randomized algorithm? What is this even, a randomized algorithm? Today we'll adopt the very simple perspective that a randomized algorithm is actually nothing but a probability distribution over deterministic algorithms. Why that? Because you could think about this, and you can think about any randomized algorithm as in advance drawing all the coin flips that it will ever need throughout the execution, and then on these coin flips running deterministically. So this randomized algorithm, this deterministic algorithm would kind of take as further input the outcome of these randomized coin flips, and then it is actually nothing but, again, a deterministic algorithm running on this particular instance. So we can say that a randomized algorithm capital A is a random variable taking values in this set script A, so in this class of deterministic algorithms. So this is something you want to be careful about today. We now have three versions of A. We have the script A, which is the class of algorithms, and then we'll have a small a, which is just an element in this class. So this is just one deterministic algorithm, and then we have a capital A, which is a random variable taking values in the set script A, so taking values which are again small a's. I agree that this might be confusing from time to time, but we'll do the same thing with the axis. So we again have a script x, which is a class of instances, and then we have, so far we have small x, which is a possible instance, and we'll also have a probability distribution over instances later. But before we get there, let's now say, okay, algorithm A's worst case cost is take the worst small x and see what is the expected cost that we will be seeing. So in this expectation, we draw one of these deterministic algorithms, and then we ask what is the cost of this deterministic algorithm on this instance. And over all of these, we take the worst of the instances. Quite importantly, this instance does not know the random coin flips of the algorithm. It is not that we write here the expectation of the max, but the max of the expectation. This is really crucial. So, as the way we can see it, somebody fixes an instance for us, and only then we flip all the coins and we draw one of these algorithms to execute on this instance. And what we want to do is we want to understand this quantity. Eventually, this C we might also think about as the competitive ratio, for example, or the ratio of how good is our algorithm on this particular instance compared to the offline optimum. And the question is now, how can we bound this? And the amazing thing is, we can do this in a different way, and this is Yao's principle. We let capital A, as before, be a random variable with values in this script A, and we let capital X be a random variable with values in script X. Then we have the following. Take this algorithm's worst case cost. We have the expected cost of our algorithm on a fixed instance. This is at least the best deterministic algorithms cost on this randomized instance. There are two things. One is proving this, which is pretty trivial. The other thing is understanding what this means. And this is much more important in what we're doing today. So what does this mean? We have a randomized algorithm and we have a probability distribution over instances. And now we say, okay, the worst case cost of this algorithm taken over all possible instances, this randomized algorithm. So take the worst instance. What is the worst instance regarding the expected cost of this algorithm? This will always be at least the following. Take your randomized instance, so you have your probability distribution over instances, and now ask yourself, what is the best algorithm that you can see on these instances? And the second thing here is at most this first thing. Why is this super helpful? It is super helpful because rather than talking about randomized algorithms, here we are only talking about deterministic algorithms. And we are only making statements about one fixed probability distribution over instances. So all we have to do is, the only point that we have to make is, there is somehow this difficult probability distribution over instances so that every deterministic algorithm always performs poorly on them. This is how we will derive our lower bounds. But before we get there, let's first prove this claim. And this is actually nothing mysterious because all we do is we plug in the definitions of the expectation. So by the definition of the expectation, what do we have? The expected cost of the randomized algorithm on this deterministic instance small x. Careful, this is a small x. This is something we can just write down. It's the probability that we actually use algorithm small a, and then we see the cost of this algorithm on this instance. And we can also write down the expected cost of one fixed small algorithm small x on a randomized instance. So this is now a capital X. And we can write this just the same way. What's the probability that we see this particular instance times the cost that we incur on this instance? Now, let's start in this statement here from the left-hand side. What's this left-hand side? This we can rewrite using the definition of the expectation. And then this will now be at least how much? Well, we could not, instead of taking the maximum, we could also draw one of these x's from the probability distribution as defined by capital X. Now we can swap the sums. And we'll see that this is again at least as much as the minimum taken over all small a of this sum. And this is exactly the minimum of over all small in a, the expectation of C of a comma capital X. And how did these two steps work? Well, there we're using that the sum of these x and small x, the probability we see small x sums up to 1, respectively the same thing for the a's, namely that these probabilities sum up to 1. So here we're taking the maximum, and here we're actually just taking a weighted average, where the sum of the weights sum up to 1. And here, again, we are taking a weighted average, and we're comparing this to the minimum. And this way, we have already proved this theorem. Good. So, as I was saying, there's actually nothing really mysterious about this proof. I think the more important thing is how can we make use of this theorem. Before we get there, let's maybe just write down one more observation, namely, if we let capital A be a random variable with values in A and we let capital X be a random variable with values in X, then we can also say that the minimum of all X in X, taking now some profit that we might get, is at most the maximum over all algorithms, the expected profit that we would get on a random instance. So this is the same thing as what we had before, but turning everything around. Now we are interested in a profit maximization problem rather than a cost minimization problem, and then everything just turns around. You swap the min and the max and you turn around the sign and everything still is true. And why is this? We might just set the cost equal to minus the profit in the theorem. So sometimes this version will also come in handy. What we want to do next is we want to see how can we use these techniques to get lower bounds for algorithms. So how can we show that there is no constant competitive algorithm for online set cover, not even a randomized constant competitive algorithm? Now we want to use Yau's principle to show that there is no constant competitive algorithm for online set cover, not even a randomized one. More precisely, we'll show the following. We'll show that no algorithm for online set cover is strictly alpha competitive for alpha being smaller than 1 plus a half times log to the base of 2 of n. N, I hope you remember, is the number of sets that we have in our set system. You can also compare this to the competitive ratio that we had for our final algorithm. So our fractional algorithm had indeed a competitive ratio of O of log n, and our final algorithm, our integral algorithm, had a competitive ratio of O of log n times log m. If I'm not mistaken, it is still an open problem to figure out the exact best competitive ratio. I think there might be even a better lower bound than what we're showing here, but what strikes me as important is the technique of how can you even show this for a randomized algorithm. And for this, we will use Yau's principle. But before we get there, we will devise our set of instances. So what kind of sequences are we considering? So to prove the theorem, we consider n only as powers of 2, and we now construct the universe U and the set system S as follows. We take a complete binary tree of 2n minus 1 vertices. The height of this tree is log to the base of 2 of n plus 1, and we have n leaves. So what does this look like? If, for example, n is equal to 8, then we have one root vertex. There are 2 children. Then we'll have another 2 children of each vertex, and eventually we end up with n leaves. And now potential elements of the universe are all nodes in this tree. But we won't have to cover all of them. Our actual universe will only be the subset of this. Namely, it will be one path from the root to one leaf. So in this picture, this will be only 4 vertices, which then will be our universe of elements that will have to be covered. Or more generally speaking, we'll just have 8 vertices. So this, for example, might be our actual universe. The sets S correspond to the leaves, and each leaf covers all its ancestors. So initially, we of course don't see at all the universe, because the universe is revealed to us one after the other. And what will happen is we'll see the vertices from the top to the bottom, so starting from the root. The first vertex that we'll see, the first element of the universe, will definitely be the root. But then we might see this or this element. But before, we'll have to choose how to cover the root. And we can do this by choosing one of the leaf nodes. Initially, all these just look exactly the same. So at this point, we have just n possible sets, which are each able to cover the one element that we've seen so far. They look exactly the same, and they also have the same cost, namely 1. But then it turns out that if, for example, this will be the next element that is revealed, that if we have chosen any one of these, then we are in the unlucky situation that this element is not covered, whereas if we have chosen one of these, then this element is covered. And what you see is that, okay, there is this one set which covers everything. But this, we don't know in advance which one it is. Good, so the sequence will be a set U of nodes from the root to one leaf, starting from the root going down. And what is the offline optimum? Well, we can cover the entire universe with only the set S corresponding to the final leaf. And I think I forgot to mention that we say that CS is equal to 1 for all S. So we'll have that C of opt of sigma will be always 1. But what is now our claim? Our claim is that there is always a sequence for any algorithm. There is a sequence such that the expected cost of this algorithm on the sequence is at least 1 plus a half times log to the base of 2 of n. And this is true for even for every randomized algorithm. In the notation of AaU's principle, we claim that for every capital A, the maximum of the expected cost of capital A and small x is at least 1 plus a half times log to the base of 2 of n. Good. So the offline optimum is always 1 in this case, so all we want to show is that for every algorithm there is a bad instance of this kind on which the algorithm will perform poorly. And how do we construct this bad instance? We could now, of course, do what we've always done, namely consider one algorithm and do like weird case distinctions of what this algorithm is doing. But we'll now do a much smarter approach because now we also want to cover randomized algorithms. And what we do is we define a probability distribution over these instances so that no deterministic algorithm will be able to do something smart. And how do we do this? Well, we now have many instances which look the same, and so the rule of thumb is always make everything equally likely, which looks the same. So how do we do this in more detail? We now let capital X be defined by choosing one of these instances meaning one leaf that we will be reaching, because we are only considering these instances which are paths from the root to the leaves, to one leaf. and now we choose one of them uniformly at random. And now Yau's principle tells us that the worst instance for our randomized algorithm that we're currently considering, the worst case performance of this algorithm is at least the performance of the best algorithm on this random instance. So what we claim is that this here, this is at least 1 plus a half times log to the base of 2 of n. Good. How would we want to show such a claim? Why would this be true? Well, what we now have to do is we'll have to understand what is it that a deterministic algorithms, take any deterministic algorithms, we now have our random sequence, which just is defined by draw one of the leaves at random and then present the respective sequence. What's the cost that any deterministic algorithm will have on this sequence? Before we do this, let's understand what this way of generating a sequence means. We can also interpret this in a different way. So an alternative way of generating this random instance X would be on each level we flip a coin. And we go left or go right with the same probability. So how can you think about this? Once again, this would be what our tree looks like. And now rather than drawing one of these leaves here at the bottom, we'll start from the root and then we'll now go left or we'll go right with the same probability. So this might now be our next one. And then again we go left or go right with the same probability. And this way we then end up with, for example, this path. Why do we do this? Because now this way of writing this probability distribution is much more in line with what the algorithm knows. The algorithm actually does not know the leaf, but it gets additional information. And if we write it this way, which is just the same way as saying, okay, we draw one of these leaves at random, but then we say, okay, in the tth step, the algorithm knows the first t coin flips. And based on the first t coin flips, the algorithm has to make a decision. If we now consider the cost, or if we now consider any deterministic algorithm on this instance, an algorithm that we want to call A, now we want to bound the cost of this algorithm A on the random instance generated this way. And if we're able to do this, then just by Gauss' principle, we have a lower bound on the cost of any algorithm, of any randomized algorithm, on the worst deterministic instance that we have here. To simplify our life, I don't actually mean any deterministic algorithm. I mean only lazy algorithms, which means that we never should choose more sets than we have to. This is kind of without loss of generality, because algorithms that choose more sets than they have to, you can actually reduce their cost by saying, okay, if you don't need to pick any set now, then don't pick any set. If you have to pick a set, then pick only one of the sets rather than many. This is without loss of generality, because you can just transform any non-lazy algorithm into such a lazy algorithm and only reduce the cost. This is a standard exercise. Good. Now let's take such an algorithm. And what will happen now? This algorithm is now presented the root node. And what will this algorithm do? It will have to cover the root node, because the root node isn't covered yet. What can the algorithm do? Well, it can just choose one of these leaves to cover the root node. Good. This will definitely cause a cost of 1. And then we go to the next level. Say this will be the next element to be covered. What happens? Well, it now happens that with probability 1/2 we get to see we have to cover this, or with probability 1/2 we have to cover that node. And regardless of what the algorithm chose, it will now have to choose another set with probability 1/2, because if the algorithm chose something here to cover the root node, then it will be bad if this comes, and if the algorithm chose something here, then it will be bad if this is the next element to be covered. And this is why our algorithm will have a cost of 1/2 in each step, except for the first one, where the cost is always 1. And this is even regardless of what algorithm we choose here. So we call CT the cost of the algorithm in the tth step. This, of course, is a random variable. We have C1 equal to 1 because the root has to be covered. And for t bigger than 1, we claim now that the expectation of Ct is exactly a half. And the reason is that A has chosen exactly one set that covers the element t minus 1 in the sequence. This is where we use that this is a lazy algorithm. The algorithm has chosen only exactly one set that covers the element that we've just seen. And now we see one of its child nodes. And we now have that with probability a half, element t also belongs to this set, with probability a half, it does not. So the expected cost will be exactly a half. What does this mean? The expected cost that our algorithm small a incurs on this random instance, this is nothing but taking this sum of all these Ct, already having used linearity of expectation here, and now this is exactly 1 plus h minus 1 times a half, and this is exactly equal to 1 plus a half times log to the base of 2 of n. And this holds for any deterministic algorithm. By the way, this would even hold for any randomized algorithm, but we don't have to talk about randomized algorithms here. Talking about deterministic algorithms is just enough by Yau's principle. So once again, how did the proof work? We said that in every step of the random sequence, the randomly generated input sequence to the algorithm will incur a cost of a half, just because with probability a half, it just has not covered the newly arrived element, because at no point it took more sets than it needed, so it did not cover an element twice. As I was saying, this is without loss of generality, because if it had covered an element twice, this would only increase the cost would have only increased the cost earlier, and you see that the argument is much easier for us by having said, okay, please don't do this. If you want to do this, you can still choose the set later. Good. And why do I feel this is easier to argue than arguing about randomized algorithms? Because everything was deterministic, or the algorithms choice is deterministic, and also we don't actually have to care about how the instance gets generated, or we can just redesign this in a way so that everything that happened before we don't care about, and then there's just this one coin flip happening in the tth step, which makes now the change between whether we now have to have a further set or not. And interestingly enough, the offline optimum isn't even clear at the beginning before the coin flips, it's only clear after the coin flips. But that's the nice advantage of the offline optimum, that it doesn't have to care. That the offline optimum can just see the entire sequence and then choose what it wants to choose. Next, we'll do kind of the same argument for ski rental, for which we use more or less the same approach, again making all algorithms look more or less the same, which is always a good rule of thumb. And also there we can derive a lower bound for randomized algorithms. Now we'll also show a lower bound for the ski rental problem for any randomized algorithm. And this bound will exactly match what we derived as an upper bound for our randomized algorithm, which we developed via the primal dual framework, which helped us to derive a fractional algorithm, and then via randomized rounding. We will not follow the template by Yao's principle exactly. We'll deviate a bit from this, but we'll still stick to the general spirit of these arguments. So what's the theorem that we want to show? We want to show that for a fixed B, no algorithm for ski rental is alpha competitive for alpha being strictly smaller than 1 minus 1 over b to the power of b to the power of negative 1. This is exactly the term that we derived also as the positive result. Good. How do we prove this? Well, we again want to devise a random instance for which then we see it doesn't care which algorithm we use. All algorithms are equally bad or so. All deterministic algorithms. Let's start with this. So, what are instances now? An instance just corresponds to the number of skiing days. So for the offline optimum, the cost that it incurs on instance x is simply x if this x is smaller than b, and otherwise it is b. And what does this mean? This means that for any random variable capital X, the expected cost of the offline optimum, crucially, the offline optimum, as I was saying, always knows the outcome of the random variable. So if this x takes values from t to b minus 1, then we'll have value t. Otherwise, we'll have a value of b. And this we can also write as follows. We can also just take the sum from t from 1 to b as the probability that x is at least t. This is just rewriting this sum here. We can also write it as the sum of these probabilities that we have values of at least t. And this then, the rest we get from here. Good. Now, what is a deterministic algorithm for ski rental? It is just described by some non-negative integer, which is simply the number of days of renting skis. Which means that the cost of algorithm A, if there are x skiing days, is simply x. If it rents skis for A days, or it is A plus B if x is greater than A, because then it buys the skis on day A plus 1. So we can also write down the expected cost of any deterministic algorithm on our sequence x. How would we get that? Well, we would now take the sum of all t from 1 to a, then we get t times the probability that we have that x is equal to t plus a plus b times the probability that x is greater than a. And this we can write also as the sum of t from 1 to a, the probability that x is at least t plus b times the probability that x is greater than a. And now what we'll do is we'll construct a random we construct a random instance, or in other words, a distribution over instances, so that each algorithm will have the same cost. This is, as I was saying earlier, this is the general rule of thumb. Make a random instance so that you really don't know what to do, because all your algorithms just are equally good or equally bad. So what does this mean in this case? So we construct a distribution over the number of skiing days so that all algorithms have the same cost. have the same expected cost, I want to say, because they might, of course, be different depending on the actual outcome. But what does this in particular mean? We want that the expected cost of algorithm A minus 1 on instance X is exactly the expected cost of algorithm A on instance X. And what does this mean? Well, we have something here on the left-hand side, something here on the right-hand side. Both follow these formula. So we can now write down what we have here on the left-hand side. There we just take the sum to A minus 1. And we have the respective sum here on the right-hand side, where the sum goes to A. Now many things cancel. For example, this here on the left-hand side, this corresponds to the first terms in this sum. So what remains is this here on the left-hand side, only the term for A here on the right-hand side, and this final term here. How big are these things? Well, this here, this is just the probability that X is at least A. This here, this is the probability that X is at least A plus 1. So we get to the point that the probability that X is at least A plus 1 should be 1 minus 1 over the probability, 1 minus 1 over B times the probability that X is at least A. So if we now set the probability that X is at least T to be 1 minus 1 over B to the power of T minus 1 for all T, then we have exactly what we wanted, namely all algorithms are equally good or equally bad. So the number of skiing days we now draw from this distribution. So with probability, what does this mean? For t equals 1, we have here, this is 1, so with probability 1, we have at least 1 skiing day. But we have 2 skiing days only with probability 1 minus 1 over b. We have 3 skiing days or more with probability 1 minus 1 over b squared, and so on. Another thing is, on this instance, when would you want to buy your skis? Actually, you don't know. It's always, at any point in time, it's not likely that your instance, that this was the, or it's just equally likely that this was the last day of skiing. So you've just gone skiing, and now it is always equally likely that this was the last day of skiing. So this is why you actually never are at the point that, okay, now I can buy the skis or so. And what does this now mean? Well, for this choice of x, we on the one hand have that the expected cost of the offline optimum, or we derived a formula for this long time ago. Here it is. So this is by our formula this much. And if you now do the math here, then you'll see, okay, this is b times 1 minus 1 minus 1 over b to the power of b. Whereas for all a, we have that the expected cost of this algorithm on the random instance. So now again, we want to use our formula for this. How much was this? Okay. This is the formula that we want to apply now. So we will have the sum of t from 1 through a, 1 minus 1 minus the 1 minus 1 over b to the power of t minus 1 plus b times 1 minus 1 over b to the power of a. And if you do the math here, then you'll find out that this is always b. Okay, so this means that there is no good deterministic algorithm in this setting. For every deterministic setting, the expected cost that this algorithm incurs is a factor b higher than what the offline optimum incurs. But what does this mean regarding randomized algorithms? We actually want to show that for every randomized algorithm, there is a small x, which makes its cost high. And now we'll actually just mimic the proof of Ya's principle for this. We'll just do a proof by contradiction. Suppose that randomized algorithm A is alpha competitive for alpha being smaller than this factor. Then of course we would have that the expectation of a comma x be smaller than alpha times the cost of the offline optimum, for this for all x. So in particular, if we choose a random x, so we would have that the expected cost for a randomized algorithm against this random x, this would of course be at most alpha times the expected cost of the offline optimum of this random x. Now this here we know is b times 1 minus 1 over b to the power of b. And what do we know about this thing here? Well, this is nothing but draw a random algorithm and now ask yourself, what is the expected cost of this algorithm on the random instance? And this much here, this is always b. So regardless of what we're getting here, this will always be b. And this is a contradiction if alpha is smaller than 1 minus 1 over b to the power of b to the negative 1. And this proves our theorem. And so we're done here. Once again, the idea was to make all deterministic algorithms look the same. So whatever choice the deterministic algorithm has against this probability distribution, they all look the same. These algorithms all look the same. This is the same idea that we also applied for the set cover problem. Here, this was a little different because, well, we couldn't use Yau's principle as it is, because this was only making statements about the algorithm's cost, and here were actually interested in the ratios, so this is why we just used the general idea of this. I now wrote this as a contradiction, but this is actually not necessary. You could also just do the same things with the min and the max that we used in the proof of Yau's principle. You would still get to exactly the same point here. Good, so now we know how to derive lower bounds for randomized online algorithms. By the way, this is not crucially only for randomized algorithms, this is also, this is not crucially for online algorithms, this is also useful in other settings, but the idea is always design a probability distribution, and this was maybe even not explicit enough in what we did today, this probability distribution is even known to the algorithm. Even if you tell the probability distribution to the algorithm doesn't really know what to do, because all choices are bad or at least equally good. So this additional knowledge of the probability distribution won't help the algorithm. This is at least what we did in the ski rental algorithm, in the ski rental example, and also in the set cover example. So if you're supposed to design a lower bound yourself, this is the way you can think about this. I now design some probability distribution that instances will be drawn from, and this probability distribution should be designed in such a way that I can tell it to the algorithm, but the algorithm still doesn't know what to do. This is very powerful because you now don't have to think about anymore about the thing that, okay, how much does the algorithm know? Maybe, this is usually the best way to think about this, is, well, even the offline optimum isn't set in stone at the beginning. But in every step of your online process, you once again flip a coin and then you only see how things continue from here. In the case of set cover, we did this in a really easy way so that even the value of the offline optimum didn't even depend on the random coin flips. And therefore the offline optimum was always the same. Here in the second part, in the ski rental example, the offline optimum actually depended on the instance. So the value of the offline optimum, the offline optimum itself, of course, always depends on the instance, but here even the objective function obtained by the offline optimum. This is it for today. Please reach out to me if you have any questions. See you next time. Stay safe in the meantime. Bye.